have the official definition of a rational function is if you have one polynomial divided by another polynomial. And for the most part, ours are mostly going to be like parabolas and lines, maybe the odd x cubed graph in there. And what we're going to do today, and what we're going to look at over the next 2 classes, is how do we graph rational functions, and what are the characteristics, okay? So characteristic number 1 is the non-permissible values. Non-permissible values result in one of 2 things. Most of the time, they're going to be vertical asymptotes. Sometimes they're going to be holes or points of discontinuity. So the first thing we're always going to look at in a question is we're going to factor it completely. This function here has already been factored completely. Okay? Once it's been factored completely, we're going to look at the non-permissible values. And in this case, our non-permissible values, x can't equal 3 and x can't equal -1. And once it's factored, we check, does anything simplify? And in this case, nothing simplifies. Like x plus 3 has to be exactly the same on the top and the bottom to simplify away, and it doesn't. So our non-permissible values stay, and whenever our non-permissible values stay, you will always get vertical asymptotes. So on this graph, there is a vertical asymptote at -1, and there's a vertical asymptote at 3. The second example they have here, we have a non-permissible value that x can't equal 3, but if we look at this question, there are factors that are identical. So we are always going to want to factor first, and any time that something factors out, you will always get a whole. And your whole will have that same non-permissible value. The x value can't be 3, so that's where the whole is. And to get the y value of your whole, you're going to have to plug into, right? Once this simplifies, I would get this new equation. The x minus 3's are gone. Now I just get y equals x plus 1. Right, maybe not new. So I plug in x equals 3 into my simplified equation. 3 plus 1 is 4. That's telling me where my whole is going to be. So this is a graph, right? Once it's simplified, y equals x plus 1 is y equals mx plus b. You know how to draw y equals mx plus b using the y-intercept and the slope. But we have, in this question, we can label it on here, a whole, which we show by an open circle at 3, 4. Now what we're going to do in today's lesson, a little bit different, is after these characteristics, it goes to example 1. We are going to look at all of the examples, all of the characteristics all together, and practice graphing all of them right from the beginning. Because that's the main purpose of this last section of the unit, is to be able to graph things. This is probably the easiest example to graph, because once it's simplified, it turns into a line. You already know how to graph a line, so you just graph your line and add the whole to it. Here they have an interesting situation where the non-permissible values, x can't equal 3 and x can't equal -1, one of the x minus 3's cancel out, but you still have an x minus 3 as a non-permissible value on the bottom. So usually, when a non-permissible value cancels out, it becomes a whole, but it only becomes a whole if it goes completely away. If a non-permissible value stays in the simplified equation, it will always end up being a vertical asymptote. Okay, so we're going to let's see. Should we graph example 1? No, we're going to wait. We're going to look at characteristics 2 and 3. When do graphs have horizontal asymptotes? When do they have oblique asymptotes? Okay. So for this, I'm going to develop some shortcuts for you guys. Okay. If the degree is larger in the denominator, in other words, here we have an x to the 1, we have no x's on the top. If you had an x on the top and an x squared in your denominator, then your degree would be bigger in your denominator. Whenever this happens, you will always have a horizontal asymptote at y equals 0. And I mentioned this before, but I'll say it again. Horizontal asymptotes tell you what's happening at extremes, at end behavior as x gets very big, either positive numbers or very big negative numbers. So what happens here, if I put in a huge number for x, I would basically have -4 divided by 1,000,000,000. Can you see that that gets close and close and closer to 0? The bigger the number you put in, dividing -4 by a huge number will get closer and closer to 0, so there will be a horizontal asymptote at y equals 0. The shortcut is, anytime the degree is larger in the denominator, you'll always be dividing by a very big number on the bottom. Will get you closer and closer to 0. So on this graph, we can add in that there would be a horizontal asymptote at y equals 0. Notice in this equation that from our first characteristic, that we have a non-permissible value at -4, and it doesn't cancel out, so that would become your vertical asymptote. So the first thing that we're doing is we're deciding where the asymptotes go. Then we're going to be able to draw these graphs with a few more characteristics after this. Okay? So, degree is larger in the denominator. Second, if the degree is the same, then you will have horizontal asymptote at y equals, and to figure it out, I'm going to put quotation marks around this and put it in green because it changes for every equation. But the idea is that whatever your biggest degree is, in this case, it's an x. You take 2x divided by x, and that's where your horizontal asymptote would be. So in this case, it would be y equals 2. Here's another example. I could make a parabola on the top, 3x squared plus 5x. And I can make a parabola on the bottom, 7 minus 2x squared. Do you see that I have it? Highest degree on the top is an x squared. Highest degree on the bottom, x squared. We have degree of 2 on the top, degree of 2 on the bottom. So my horizontal asymptote, and in this one, I have a 3x squared on the top and a negative 2x squared on the bottom. Its horizontal asymptote would be at 3 over negative 2. Again, the shortcut is good enough. The textbook goes into a synthetic division way of trying to explain it. You can read that if you'd like. But the idea being is that as x gets really, really big, okay, the minus 3 and the minus 1 won't matter very much. If you have $1 billion and you lose $3, big deal. If you have $3 and you lose $3 and you need to go home on the bus, it is a big deal, right? But if you had $1 billion in your pocket and you lost 3, you probably still could get home on the bus. You probably wouldn't want to take the bus. $1 billion in your pocket. But same thing when the degrees get bigger. Even though putting in 1 million for x, and on the top I would have 5 times 1 million, which is a big number. It actually doesn't matter much when you compare it to 1 million squared. So you can ignore everything except for the values that have that highest power, because when numbers get really, really big, those will be the only things that will affect it. And you could just look at the coefficients. So horizontal asymptotes. Type 1 is the degree is bigger in the bottom, then it's at y equals 0. Type 2 is when the degrees are the same, then you're just looking at the coefficients. So we had degree bigger on the bottom, degrees the same. The last thing that we look at is when the degree is larger in your numerator. And this will result in an oblique asymptote, except if it simplifies, because we had, right, we did an example, characteristic number 1. We did an example with a hole. It started off with an x squared on the top and an x on the bottom, but once it simplified, it just turned into a line. Then we'll graph the line with the hole. But if things do not simplify and the degree is larger on the top, then you are going to get an oblique asymptote, which is a diagonal asymptote. The diagonal asymptote, you will need to use your skills with synthetic division to find. You will actually divide the x squared, which is 1x squared and then 0 and then 0, divided by x plus 1, so you put a negative 1 outside, bring down the 1, bring down the 1, multiply and add, and your result is y equals x minus 1 with a remainder, and you can ignore the remainder, and whatever equation you get, no matter how big that remainder is, you can ignore it. The equation that you get this will be your diagonal or oblique asymptote. Okay, so we have those three characteristics of diagonal or oblique asymptotes. And now we are going to go to example 1. And the first thing I'm going to get you to do is write these steps down. We're going to use these 5 steps for all of 2.3 and all of 2.4. And now till the end of this unit, we are just going to be practicing graph. And each of these steps, when we see some examples, they will make even more sense for you. Make these a little bit smaller so we still can see them off to the side here. So our first step is always going to be factoring something completely. So in equation A, we notice the top is a difference of squares. There it is, factored completely. Okay? We then list our non-permissible values. In this case, x can't equal -5. And that takes us to step 2. Step 2, in listing the non-permissible values, we have to determine, is the non-permissible value going to be a whole, or is it going to be a vertical asymptote? So we look after it's factored. Sure enough, we have 2 factors that are identical. That gives us, once it's simplified, a new equation, which I'm going to write here in blue. And since the non-permissible value has simplified and gone away, we have a whole at x equals -5. And to find the y value of the whole, we get that from our new equation because we can now plug in -5 into that new equation. -5 minus -5 is -10. So in our steps, we list the non-permissible values and determine if they're wholes or vertical asymptotes. And then in green in the step, it says, if there is a whole, which is in our situation it does, you graph the simplified equation, which is the blue part, and add the whole. So now we have to graph the blue part. The blue part is no longer a rational equation. So we don't have to worry about steps 3, 4, and 5, because now in graphing the blue part, it's just a regular line. You know how to graph lines. What you're going to do when you graph this line the y-intercept at -5 we are going to label our whole make a big open circle where the whole would be at -5, -10. If you have 2 points, that is enough to draw your line. Put arrowheads on the end, and your graph is done. Other points you might like to graph in here, you might like to label as well your x-intercept. How do we find an x-intercept? We plug in 0 for y and solve. Your x-intercept would be 5, 0. So this is an example where we have a hole. When we have a hole, that green note comes into play. You graph your new equation. Sometimes your new equation is still a rational equation, and you still have to go through steps 3, 4, and 5. In this situation, it was just a line, so then you could just graph it as a normal line. When we look at part B, y equals 4x plus 2. You could factor out a 2 out of the top, giving you 2 times 2x plus 1 divided by x minus 2. Step 1, factoring completely. Then list your non-permissible values. X can't equal 2 because that would cause you to divide by 0. Does the x minus 2 cancel out in this situation? No. I'm just going to steal our steps so that we can see them as we're going here. So we factored completely. We listed our non-permissible values. Since it doesn't go away, we have a vertical asymptote at x equals 2. When you're listing a non-permissible value, you put the line through the equal sign, because a non-permissible value, you're saying x can't equal 2. But the equation of the asymptote is always an equation. So the equation of the asymptote is x equals 2. Okay. Now we get to step 3. Determine if there is a horizontal asymptote or an oblique asymptote. So in this question, right, we noticed that we had the same degree on the top, the same degree on the bottom. There's an x on the top, there's an x on the bottom. That means you will have a horizontal asymptote at, and I'm going to first write it this way. On the top we had a 4x. On the bottom we had an x. Simplifying that. Your horizontal asymptote is going to be at y equals 4. So that's step 3. Determine if there's horizontal asymptotes or oblique asymptotes and find them. We are very close to starting to graph this. In fact, once you have your asymptotes, I would say put them on here. We know that we have an asymptote vertically at x equals 2, and we know we have one horizontally room. At y equals 4. Step 4. We need to find some points. The points that you're going to find always are going to find your x-intercepts and y-intercepts. And then I have in brackets a few other nice points as needed. And you need 1 point per section. So what does this mean? Well, first, let's find our x-intercept. Or sorry, let's find our y-intercept is the easiest one. We'll start with the easy one. First, we're going to find our y-intercept. How do you find the y-intercept? You plug in 0 for x. Go to our original equation. It was 4x plus 2. So 4 times 0 plus 2 over x minus 2. So that would be 0 minus 2. And so you get a y-intercept and label it at 0, -1. Next, we'll find the x-intercept. You find an x-intercept by plugging in 0 for y. And now we have to solve for x. Okay? A couple of things. Okay? A couple of maybe shortcuts, maybe not. First of all, if you have a rational expression, you have a fraction. The only time a fraction is ever equal to 0 is if the numerator is 0. 0 divided by 5, 0 divided by anything is going to be 0. So as a shortcut, some students just say, I just need to look at this. I just need to find out when is the top equal to 0. Mathematically, I hope you can see this, because if you are actually solving this, the first thing I would tell you to do is get rid of your fraction by multiplying both sides by x minus 2. That would cancel these out. This side would still be 0. And that's why so many students just say, oh, I just need to make my numerator equal to 0. Even if I show the algebra and I multiply both sides to get rid of the fraction, I just end up with my numerator equal to 0. Solving this is not hard. Move the 2 over and divide by 4. You'll get -2 over 4, which reduces to -1/2. And we can label that point as well. So step 4 says, do all of your intercepts and nice points 1 point per section. So when I talk about a nice point and 1 point per section, your graph will be separated into sections by your vertical asymptote. We would say that this graph has 2 sections, the section where x is less than 2 and the section where x is bigger than 2. Do you notice that we have 2 points already in the section where x is less than 2, but we have no points in the section where x is bigger than 2? So when you want to find a nice point, and you were choosing something you could plug in, you'd probably plug in 3 or 4, some nice number bigger than 2. You probably wouldn't choose to plug in 2.718 and do the mental math for them. So for our nice point, I'm going to plug in 3 and find out what I get. So I go to my equation. If I plug in 3, you see that you would get 1 on the bottom. And on the top, you would get 2 times 3 is 6, plus 1 is 7, times 2, 14. If I plug in 3 into the original equation, I get the point 3, 14. I go up somewhere on my graph, approximately to scale. I label 3, 14. Once you have 1 point per section, you are now able to draw the graph. To draw the graph, you just need to have, well, the section where your points are. Obviously, your graph is going to go through these points. I hope you can see that the graph is going to connect between those two, but then you just need to draw it towards your asymptotes. So this one will go up towards this one and then down towards that one. That's the last step. Just draw your graph towards your asymptotes. You can, if you found x-intercepts, your final graph can't add any more x-intercepts. You have to be careful with that. You found all your x-intercepts. There will not be any more x-intercepts once you've drawn your final graph. Okay. Questions for practice are number 5. And when you're doing question number 5, even though it says Question number 5. Says, for each graph, just write the coordinates of the whole and write the equations of any vertical asymptotes. I actually want you to graph them completely. Okay? So I would like you to draw the complete graph for each of them, following these steps all the way through.